Well, thanks for asking the question there. I'm not too sure why actually we're in this particular session. So if you want the short answer, it's yes, and you can leave if you want. No, but in seriousness, I thought I'd better explain a little bit about the New Zealand dairy system. Now, something that may surprise many people is that New Zealand operates under a system of absolutely no payments, no subsidies, whatever, and this is where my European colleagues go, what? No, but it means that the New Zealand dairy farmer is very adaptive and they're usually very efficient, and they have to be because we have some of the world's very hardest water quality policy to align yourself with. Which makes my job quite interesting when I'm provided with that question. I have to go out and provide people with advice on how to farm profitably, and I also have to advise people on policy as well. I figure that if I'm pissing them both off equally, then I got it about right. So, we have to be reasonably adaptive because we have a very varied climate. You can go 100 miles from farming in what is effectively a temperate rainforest, 4.5 metres of rainfall a year. The other side of the mountains, you only get 200 millimetres. Very important for New Zealand systems, they're outside, they're grazing all year round in the majority of the country. We have to maintain with our varied soil types relatively enriched soil test phosphorus measured as Alton P. But as a consequence of this, we have varied losses not only in terms of nitrogen, but also in terms of phosphorus. Now, what are some of these causes? It took a while for me to get these girls to line up, but eventually they did. Now, start off in the mid-70s, only 2 million cows. Now we've got more than 6 million. That's more than people and hobbits. Now, commensurate with that, dairy, it was the #1 earner for us. It's now #2, with tourism being #1, but it occupies still about 20% of our GDP. Of course, there comes a bit of a price with that, in that we're seeing, what you'll see here, both an increase in the nitrogen, but also in the phosphorus surplus. Now, compared to most row-cropped or arable systems, the issue is not really about the surplus, it's about how it's utilised by the animal, and this is giving you an example here. So, just the fertiliser component itself, applied as urea, results in significantly less than if that urea is grown as pasture, then cycled through the animal, comes out in the urine patch at a rate of about 1,000 kilos of N per hectare. That's 850 more than the pasture can take up, and of course the rest is lost and exacerbated as more you put on. So, with phosphorus, we're seeing a transformation of land use from our fine furry woolen friends here into dry stock all the way through to now irrigated in those areas where you get 200 to 400 millimetres of rainfall a year. Unfortunately, it's also happening on areas that have what we call low P retention soils. And so you could say that on a scale of 0 being sands and 100% being soils that have a high concentration of iron and aluminium, allophanic soils for example, sorbing about 95%, it's occurring on soils that have sandy texture and very low P retention. So, on an annual basis, you're going from less than half a kilo of P per hectare per year all the way up to 4, and I've seen some much higher. Now, I'm going to give you some information about what's happening in this particular area, and it's going from, as I say, being converted through to dairy, and so the operation that I'm going to give you about 7 or 8 years of data with was converted in 2009 through to a uniform rate dairy. So, there's about 900 millimetres of irrigation going on in this system. There are 3 different soil types though. That's a centre pivot, about 1 kilometre long, so it's reasonably large. But midway through, the farmer decided that he would move through to a variable rate system because it made economic sense. And that meant that he was applying only the right amount of water at the right time. There's a daily feedback mechanism according to what the soil water deficit was. And here's the operation here in central Otago in the south of the South Island. There are two locations indicated by those upside down red triangles where we can intercept and monitor not only flow on a continuous basis, but we can also intercept and measure what's going through them. It's effectively a hydrologically isolated dairy system. That solid line around the outside indicates a stream that's being redirected, but there's still continuous flow going through and underneath this dairy operation, coupled with lots of artificial drainage networks means you're able to capture everything, both before and after it goes through this system. So, come straight to the chase. What's happening there? So, under the uniform rate application system, here it is in terms of upstream and downstream measurements. There's the median concentration in terms of two phosphorus forms, so dissolved reactive P, that's filtered, algal available, and total phosphorus. That line refers to the water quality regulations for discharge from that property, so we must comply with this by 2025. So you can see that there's an increase in both these constituents. That's to be expected. You're going to have some, what would say, leaching through into that continuous flow. And then we've also got some increases in terms of total P, probably associated with decomposition of the tile drain network. Now, under variable rate, two things have happened, and I'll explain why. In terms of upstream, there's been a decrease. But the salient point here is that there's been a decrease in both forms, both dissolved reactive P and total P, downstream compared to what was going through it originally. Nitrate, similar picture. You're seeing a commensurate increase, obviously, due to those urine patches and the leaching of nitrate through and into the shallow groundwater system. You're also seeing, because it occupies the majority of total N, an increase in that fraction as well. Under variable rate, you've seen a decrease in terms of, well, there's a slight increase in terms of, nitrate-N, but a decrease in terms of total N. The important point is, though, that he's now meeting his discharge requirements or regulation. So, total that up, though, as we do, in terms of a legislation, it's not only concentration, but it's also a loading basis. And the loading regulation in this area is around 30 kilos of N per hectare per year. And we can see here, on this basis, under uniform rate, only 20. Compares quite well to the New Zealand average. A substantial decrease in terms of the load, though, and not only nitrate, but also in total P forms. Question is, why? Well, let's look at the phosphorus component first of all. So, it took a little bit while for the fertilizer regime to bed down, and as a consequence of that, in 2009, there was a greater number or greater frequency of fields that were enriched with soil phosphorus compared to now. The average hasn't really changed, but the point is that the distribution has, and so it's not a linear relationship between soil test P, Olsen P, and P loss. It's non-linear, such that the frequency has now decreased of those very enriched fields, and so there's less bias on the potential loading. Now, it's not due to changing in fertilizer regimes, because that hasn't really changed a great deal. Indeed, stocking rate hasn't changed, although production efficiency is probably increased by about 10 or 12%. If we look at the hydraulics, and so you have here the rainfall in blue and the irrigation in orange. A couple of dry years under the variable rate system, okay, so the irrigation compensated for that. Point is, the grey line there indicates that flow is decreased by about 20%. Now clearly that is a reason for some of that decrease. And you can account for that So these are the loads for both nitrate-N and total P. Now, if you make the assumption that the relationship between flow and nitrate, or phosphorus, remains the same, but then you look at the lower flow rates in the drier years, you're able to allocate how much of that change is due to lower flow. For phosphorus, of course, there was a change in the distribution of fields that were really enriched with Olsen P. So there's a decrease as well. And I showed you that 10 or 12% increase in production. That means that there's better utilisation and uptake of both N and P in the pastures. So, get you back on time. So not only did he go from a dry land system where he was making probably about $1,500 a hectare, he's increased that by almost an order of magnitude. He's gone from what was considered in that particular area as a leaky dairy system to one which meets his compliance regulations. He's done that through a combination of less transportation, i.e. drainage, through to the shallow groundwater system, resulting in increased efficiencies with both N and phosphorus utilisation. And in the end, he's also increased his profitability. So there's been a payback in about 6 years in terms of capital infrastructure on that variable rate system. So my slightly longer-winded answer to that initial question remains the same. Yes, but there are some caveats, and I hope you ask me about them. Thanks.
Thank you, Richard. You did a wonderful job, and we have ample time to have questions.
A clarifying question. I'm curious to know why, or what could explain the higher uptake under the varied irrigation. Why did you get higher production?
Sure. So I mean, it's a very simple answer. It's maintaining the enriched concentration of both N and P within the root zone for longer periods, rather than it being lost.
So can you explain how you measured it? Like, were you measuring soil moisture in each of those segments that you showed us? Yeah,
so I mentioned there was a daily feedback with regards to the soil water deficit, and that is done again in the root zone such that it's kept probably within 10 millimetres of optimal. And so 3 different soil types, 3 different measurements, daily feedback, nozzles going on, going off. There's going to be a slight change to that system as well, and there's going to be 2 additional technologies put on there. One is that the dirty water from the milking parlour goes through a series of what we call effluent ponds, to the point where there are 3 of them. The third one has a solids concentration of about 0.4%. So it's able to go, the nutrients from that are able to be put out back through the centre pivot irrigator. He's going to couple that with some hyperspectral technology on the centre pivot itself, such that the fertigation that goes through that system has daily feedback with regards to the concentration of likely nitrogen in the pasture. And that too, during the sums, is going to pay back fairly quickly.
Thanks for the presentation. I clearly underestimated the amount of hobbits in New Zealand. I was wondering what are the main transport routes for the nutrients from the field towards the surface water?
So this is one of those caveats I mentioned, and thanks for asking that. So this is probably an idealised, idyllic system to measure a difference, okay, in that the low P retention and sandy texture are both conditions that are conducive to subsurface loss. of phosphorus. Under most dairy and or systems with a slight bit of slope, it's going to be surface runoff, overland flow effectively. You've also got here, because of that sandy texture, obviously that's conducive to nitrate transport. And many of the other systems, there would be some sort of hard pan, fragipan, by which there would be increased denitrification. So you're going to see, again, an improvement, an idyllic improvement with regards to that.